Okay, so we're going to conclude this week by looking at log functions, which, as most of you know, is the logical place you go after looking at exponential functions. So it all has to do with inverse functions. So I hope you remember doing that in algebra sometime. The idea of an inverse function is if you've got a function, you define its inverse by f inverse of y equals x is the same thing as saying that f of x equals y. So remember, a function is like, you've got a box, you put in inputs, and out you get outputs. In the inverse function, you just reverse it. So the outputs become inputs and the inputs become outputs. So it's just going in the other direction. And it's a really useful concept because it's kind of how you undo things. So for example, squaring it, you undo it by square roots. Subtraction, you undo it by addition. Division, you undo it by multiplication. So for example, if we've got y equals 3x squared minus 4, the way we do the inverse of that is, okay, well, what do we do? Well, we remember that outputs become inputs. So y would now be our input. So the first thing we've got to do to it is add 4. And then we divide by 3, and then we take the square root of it, and that's the reverse of what we do for the original function, 3x squared minus 4. Remember, first we square it. So in the inverse, the last thing we do is square root it. So it's all about swapping x and y, input and output. And so when you look at the graph, you see that it's actually mirrored along the line y equals x. And so in kind of blue there is the function f of x, and we reflect it along y equals x, and we get that black line of f inverse of x, right? So if AB is on fx, then BA is on the inverse. So logs is the inverse of exponential. So natural log, which is denoted ln, you'll find that on your calculator, is the inverse function to the natural exponential function e to the x. Okay, so what that means is that ln of a is the number b for which e to the b equals a. And it's very useful for whenever you're handling an exponent. You want to bring an exponent down, you take a log. For example, you've got this differential equation here, p prime equals 0.01p, p0 equals 38. How long does it take to double? Well, doubling is going from 38 to 76. So we want to solve the equation 76 equals 38 times e to the 0.01t. So the way we undo it is we have to get rid of that. We want to isolate t, right? So the first thing we do is we divide by 38. And so we get 2 equals e to the 0.01t. And then we have to undo that exponentiation, so we take logs. So we get 0.01t equals ln of 2. So t equals ln of 2 divided by 0.01, which is 69.3 years. And when you did logs, hopefully you remember the log laws. So things like ln of 1 is 0. Logs turn multiplication into addition. So ln of m times n equals ln of m plus ln of n. Turns division into subtraction, and it turns powers into multiplication. So ln of b to the t is t times ln of b. Okay, so now we can figure out what that k sub b is that we had before. Remember when we had, when we were taking derivatives of the b to the t, we had this constant k in front. We can now actually show that that constant k is ln of the base, because b to the t equals e to that base times t, right? Because when you differentiate both those things, you multiply by that constant k sub b. So if we take logs of both sides, on the left-hand side, we get t times ln of b, and on the right-hand side, we get, well, ln of an e to something is just the exponent. We get kb times t, divide by t, we see kb equals ln of b. So we can add to our differentiation formulas. The derivative of b to the x is ln of b times b to the x. We can actually have another new derivative law, which is that the derivative of ln of x is 1 on x. And the reason for that is all due to the fact that it's an inverse function. So we go to the next slide. So it all follows from the geometry of inverse functions because they're mirror images of each other along that. We reflect along that line y equals x to swap x and y. So if you remember, if AB is on a function, then BA is on its inverse. You look at the slope at the point AB, you get a rise over run. Okay, when you reflect that across that y equals x to the inverse function, you see that little triangle gets rotated 90 degrees. Okay, it gets flipped. And so what was rise over run before now becomes run over rise. And so if whatever the slope is at AB for a function, it's going to be 1 over that slope at the point BA on the inverse function. And so the slope of e to the x at AB is b, right? It's the y value because we remember, a is x, b is e to the x. The derivative of e to the x is e to the x. So the slope of the function e to the x is just whatever the y value is. That sort of defines e to the x. So the slope of ln of x at BA is 1 over b, 1 over the slope of what the slope was at AB for the exponential function. But 1 over b is just 1 over x. So if you look at it, b is just what the x value, what the input is. So that shows you that the derivative of ln of x is 1 over x. That's a really handy thing to do. So let's have a look at a few examples of things. So let's do a few derivatives. So, using the fact that the derivative of ln of x is 1 on x, and we're going to be using the chain rule. So, right, the derivative of ln of something is going to be the derivative of that something on top divided by that something. For example, y equals ln of 3x, then y prime equals, well, the 3x goes on the bottom, and on top goes the derivative of 3x, which is 3. So it's 3 divided by 3x, it's 1 on x. Remember, it's the chain rule, so we're letting u, in this case, u equals 3x, and ln of u, that's our chain. So we multiply the derivatives together. The derivative of 3x is 3. The derivative of ln of u is 1 on u. So that's what we do there. 3 times ln of x. Well, 3 is just multiplied out front. So the derivative of 3 times the function is just 3 times the derivative. So the derivative is 3 on x. Here's a strange little one. The derivative of ln of 3 to the x. Okay, so our chain is u equals 3 to the x and ln of u. So the derivative of 3 to the x is ln of 3 times 3 to the x. We just did that before. And the derivative of ln of u is 1 on u. So that's 1 on 3x. So put it together, the 3 to the x's cancel out, and we're just left with ln of 3. Okay, now some questions you can just answer pretty straightforwardly. So for example, the rate of growth is proportional to the population. If in 2015 the population was 40 million, in 2020 it was 45 million. What will it be in 2030? Okay, so we're told that the rate of growth is proportional to the population. So that means every 5 years, the population grows by a factor of 45 over 40. So that's multiplied by 45 over 40. Okay, so the population in 2030 will be that 45 million times 45 over 40, which is how it would grow in the first 5 years, times another 45 over 40, which how much it'll grow in the next 5 years. So that's actually that almost 57 million there. But sometimes you actually need to take logs. So suppose you have this bacterial population and the population is given by 200 times e to the 0.12 t. What is the doubling time? Well, our equation to solve is 2 equals e to the 0.12 t. Taking logs, we have ln of 2 equals 0.12 t. So t is ln of 2 divided by 0.12. And on your calculator, that turns out to be 5.78. Okay, and I'll conclude with a little bit more complicated one. So let's say we're told that sugar and water dissolves at a rate proportional to the amount left undissolved. If 40 pounds reduces to 12 pounds in 4 hours, how long till 99% of the sugar is dissolved? Okay, so let's S be the amount of sugar undissolved. And we're told that S prime equals Ks. That's that rate proportional to the amount left. Okay, and we're told that when t equals 0, we have S equals 40. So we know that if S prime equals Ks, then the amount of S is equal to some constant times e to the kt. So at the beginning, we start with 40 pounds. So C equals 40. So the amount of sugar is 40 times e to the kt. Now we've got to find k. So we're given an extra bit of information. When t equals 4, we have S equals 12 equals 40 times e to the 4k, right? Because t equals 4. So now we solve for k. We need logs for that. So we take 12 divided by 40, take the log of that. That has to equal 4k. So that means k is negative 0.3. It's good that k is negative, right? Because we're in a decay situation. So for 99% dissolved, we want 1% left undissolved. So we want 0.01 equals e to the minus 0.3 t. T is the time to get there. Again, we take logs. And so we get ln of 0.01 divided by negative 0.3. ln of 0.01 is going to be negative, right? Because it's 0.01 is less than 1. And that gives us 15.3. And actually, we're given units here, unlike in the first problem. So 15.3 hours is the time it takes. Excellent.